actual consistency protocols. Are you all awake, ready, no lunch dip? Because here we go. This is already kind of heavy-duty stuff. I'm going to look at continuous consistency, and I hope that discussing a bit about the implementation of continuous consistency will also give more insight in what this model actually is. So again, I always make the separation between the specification and the implementation, and I'm now going to look at the implementation of continuous consistency. Now, how would you implement such a thing? Well, I'm assuming I have a collection of servers. Each of these servers is S1, S2, S3, Si, etc. And each of these servers has a log, an ordinary log denoted like this. People have made the mistake that halfway the slides, people are thinking, why is he taking the logarithmic of whatever? It's not a logarithmic, it's a real log, okay, with stuff in it. Now, here's a bit of an abstraction, but I'm using this to not just stick to numbers, so to say. I'm considering a data item X, and I'm associating a weight to indicate the numerical change in the value after a write operation. To make this very concrete, if you are talking about numbers, the weight could be the ordinary increment of a number. Okay? And I'm also making one simplifying assumption. All write operations have a positive weight. And I'm going to do this to ensure that I always increase things and never add something with a negative weight, because that will just complicate matters but will not affect the essence. So without loss of generality, I can assume that the weights are larger than 0. Okay? Now this is important for the model. We have a write W that is initially forwarded to one of the N replicas. By that I mean there's a client who's going to do an update and will contact one of the replica servers and say, hey, I want this thing to be updated. And it does a write operation. And the replica server that's being contacted for that write operation is called the origin. Okay? Here it comes. TWIJ are the writes executed by server SI that originated from SJ. So the model will be that I as a client contact, let's say server SJ to be consistent. Yeah. I contact server SJ. That write will then be executed over there and eventually propagated to the other servers. And then TWIJ is nothing but an account of which write operations originating at SJ have been propagated to SI and executed over there. Formally, that's this thing. TWIJ, who could, I did this with graph theory and complex networks, who can translate this for me, can translate this into ordinary English? I will record that it is absolutely silent now. It's not that difficult. Yeah, go ahead.
TWIJ equals to the sum of every weight, i.e. writes, propagations to other servers that are not the origin server. That should be the
Oh, this one over here, okay. Okay, okay. You're getting close. Just a bit of notation. So basically this is a set, okay? And the set contains weights for which it holds that and then this. Okay? So let me try to give... No, somebody else perhaps. Yes?
It's the sum of all weights where the origin of that weight is j and the log where you're writing is I.
Yeah. You could rephrase it just a bit. It's the sum of the weights of the rights that originated in Sj and which are found in the log of Si. Okay? That's it. Okay. This was simple. Now let's take a look at our Ashley data. I'm going to look at a single data item X, and the actual value, which I denote as V of t is a time, is this thing. What is that thing? Yes?
The initial value plus all the rights that happen at k.
No.
Sum of all rights. So you have like a list of rights that happen at k. And that sum you add to the initial value and then you get the value at that time.
No. That's not it. I see that I have to check my...
Sum of all the weights of rights that have happened and that can have been logged at the same server.
No. I should have repeated that actually. Okay, I'll skip this one, this repetition. I often tell people either act as a computer. That means stop thinking and just do it. That's when you execute algorithms. Don't even think. You know, just duck, 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 duck. In the case of math, I often say, don't think, just do symbolic processing. In 90% of the cases, you'll see that it works. What is this thing over here? Because that's the key to the solution. Yes?
The total number of rights that happen at the same location or server.
Let me first simplify. I think you understand. Okay, but let's decompose it. What is TWKK?
The number of rights that originate from the same server.
You can be more precise, not the same server. TWKK. Let's make this concrete. What is TW11? Let's get back to the definition of TWIJ. Now you can do your symbolic processing. So 1, 1. And then you take a look at the blue part. And then you say, exactly. Do you understand what you just said? It's the rights that were sent to server 1 and were executed at server 1. Okay? So if you take a look at TWKK, those are the rights that were sent to server SK and executed over there. Who cares about propagation? And what this thing then says is, let me take a look at all the rights that were submitted to the system. And I will only consider the rights that were submitted to what we have called the origin servers. And if I take all those rights, aren't those the total rights that I would have? There aren't any more. Agreed? So the sum of k to 1 to n of TWKK is nothing else but the total collection of rights that have been submitted to the system for data item X. Is that clear to everyone? And then suddenly this thing makes sense. Just a minute. I'll just finish my sentence and I'll come back to you. The value of X at time t is its initial value plus all the rights that were submitted to the system. That makes sense, right? You had a question.
No.
You didn't have a
Well,
question.
I had a question, but I have to look at the slide again because in the expression there is no x in the expression.
No,
So
because
it looks like it's for all right for all data that came.
no, I'm just looking now at one data item X. Yes.
What you said last different from what I said in the beginning.
Oh, that's a really tough one because now I have to.
Because I said it's the initial value plus all the rights that happen at k.
No, because okay, now because it's not all the rights that happened at K. It's all the rights that happened at that were sent to K and sent to I and K plus 1 and every server. Not just all the rights that happened at K. In fact, that would be wrong.
But you're only looking at that server, right?
No, I'm looking at all the servers from 1 to n. That's the difference. Do you understand?
Yeah.
Okay. Very important. Thank you for mentioning this again, because if you mention this, half of the people would have thought exactly the same thing. That's my ground rule. Yes?
Notation thing, so if k is 1, it will be 1, 1.
Yes?
K is 2, it will be 2, 2.
Yes?
What happens to the k originated in k, the right operations that originated in k, but shouldn't they be also implemented in the...
They're here.
executed in the...
Don't forget that K is just a variable here. It's a parameter. So I'm looking at S1, S2, S3,
So 1,
as
2,
K minus 1, as K plus 1 until Sn.
Yeah, 1, comma 2 is also included.
No, 1 comma 2 is not included. Because again, don't think just apply symbolic processing. This sum, okay, I will, this is quite elementary, but nevertheless, it is important. No, let me just write this thing here, TWKK is equal to, and just don't think, just do. TW2 2 plus TWN N.
My question is, you shouldn't want to because you're writing it...
Okay, I get your question. Is this correct? Shouldn't this also include the TWI comma J's, where I is not equal to J? Who has an answer to that? Tessa.
You're going to count stuff twice or 3 times or, well, actually n times.
Exactly. Because if you would count that as well, you would not only be counting the right operation initiated at, let's say, TWK, but that same right operation that had been propagated to SI will be counted there as well.
Yes.
But that's once too often.
You are not sure if other servers have already executed it.
That doesn't matter. No, not okay. Do you understand why?
It's not okay because if it was a bank account and you were...
Forget about bank accounts. This is math. No. But this is absolutely correct. I'm counting. I'm looking at all the right operations, and this is the correct interpretation, that have been submitted to the system. Now, I decompose what this means, submitted to the system. Well, it landed for the first time at one of these servers, right? And I have n of these servers, so I collect all the right operations where I initially sent these operations to. Those are the only right operations that the system knows about. Agreed?
But it's the same value the same variable we are acting on. All servers are acting on the same variable.
On X, yes. The actual value of x at time t is this expression. Okay?
Do they share the latest update after the write operation?
Do they share the latest update after a write operation? Okay, let's start with that. Who are they?
The server?
The other servers.
You can't make them up from this expression.
You certainly can't.
You end up with different x's. That's what I'm.
What is the model here? There is one variable x. It's not at a single server. It has been replicated across the servers. Okay? And because we're not talking about propagation at the moment, I don't know, I'll get to that in just a minute, I don't know what values these other guys have. I will bet you they will not be the same. If I don't propagate any updates, they will be different. Okay? The value vi of x at replica I is this thing. What is this thing?
How many updates of that variable I have received that weren't originally sent?
Say this again?
How many updates of the variable I have received that weren't originally sent? That were sent from the original servers.
I think you mean well. Okay.
I have two servers.
Yes?
I defined send update x to 2
Yes?
and A. So this A tells B, here's an update that I received, you should do the same.
Yes. Okay. Okay. I would reformulate it, but I think you understand what's going on. What this thing says is, now I'm looking at server SI. Okay? Now what is the value of VI at SI? Well, it's exactly this. It's exactly the write operations that have taken place on all other servers and that have been propagated to me. That's exactly TW I, K. To go back to the definition, are the writes executed by server SI that originated from SJ. In the previous expression, J is K. And I'm looking at server SI. Got it? I think this is what you meant.
But
Yes.
it's including itself. Yeah. It's the I can be
I. K can be I. Yes. Does that make sense? Of course. Those were the updates that were directly sent to me. Okay. Everybody now very familiar with these things? Your suffering is not over. What I now need to do is to ensure, and now we're talking about continuous consistency, is that the actual value of x minus that of what I see at a server is always less to a certain parameter delta I. And I'm going to make life easy. I'm going to assume that delta I is the same for every server. So it's delta. Okay? Basically, I'm saying no server is allowed to have a local value of x that deviates more than delta units from what x should really be from an external's point of view. Did everybody understand what I just said? So again, the system model. I have a system consisting of n servers. From an external's point of view, that's just a black box, right? And what I'm doing is I'm submitting writes to this black box, and every write is an update. And the only thing I do is I increment x. Little do I know that in the black box, my writes are actually being submitted to different origin servers. Okay? I don't know that. To me, it's just tuck, 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 x goes up and up. That value of x is vt. And what I'm saying is that in a continuous consistency model, I can specify that any of those servers inside that black box is not allowed to deviate from what I see from the outside to be the real value by more than delta units. That was a very long sentence. I apologize for that. Sometimes I'm glad that I'm recording this. Yes?
Won't you overcomplicate things by defining a delta for every server, not just a global for the whole system?
Yeah, I am overcomplicating things, and that's why I'm simplifying it to say that delta I is the same for every server. But this is the general model, okay? So far, so clear? Well, watch this. Every server, SK, maintains a view, TWKIJ, shit, another parameter, of what it believes is the value of TWIJ. Okay? So here I am, a server, SK, and I got to get a feeling of what's going on at server I. And TWKIJ is my belief of what server SI has seen from the updates that originated from server SJ. This should hurt a bit. Okay? Now, this is the only place where my example becomes very unrealistic, because what I'm saying is, well, how will you get to know these TWKIJs? And I'm saying, well, you can gossip things. And the assumption that would make this realistic is that updates are actually costly. They operate on complete big files, for example, and that you would have to move files around. So instead of moving files around, you move meta information on those files around, being, hey, what kind of updates did you do? And that information is spread between the servers. So the servers know what the status is of the replicated files at the different servers without having to see the entire file. Now, in the example that I'm giving, I'm just talking about a very small variable x, that can go up, 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 up. So why would you even go through the whole gossiping stuff if it's just this small variable? Well, just now think of this small variable as being big. Okay? Can somebody explain to me what this is? This is going to be the crux of our reasoning about continuous consistency. And if you just say this in English, you'll say, oh, that makes a lot of sense. Yes?
The view of a server S of another server is always less than the actual updates the server has received, which is actually less than the updates it has himself.
Thank you very much. That is completely correct. How am I going to repeat this? I will repeat it in my words, but you're absolutely right. The view, what server SK thinks about what happened at SI is always less accurate, let me put it like that, than what actually happened at SI, and which is definitely less than what really happened from the originating server. So let me repeat this again in different words. What SK believes about the state of TWIJ is always less or equal than the actual state TWIJ, which is definitely always less than TWJJ. And the difference between these two are exactly the rights that have not yet been propagated from J to I. Got it?
This whole maintaining a view, it sounds like vector clocks we discussed before.
Ah.
What does it just mean?
Yes, it's maintaining vector clocks. In fact, I'm a bit sneaky here because I'm introducing matrix clocks, a version of matrix clocks, but I haven't said this. Okay, but you're right. This is. You could also say this is, has everything to do with versioning in general. Okay. Now, what will save the day? Server SK will send operations from its log to SI when it sees that TWKIJ is getting too far from TWKK. Okay? So as soon as this thing happens, it starts pushing its updates to SI. So when we're talking about server K, when it knows about these write operations, but its view on what SI has from itself, if that is larger than delta over n minus 1, it starts pushing updates. Is this clear to everyone? If it's so clear to everyone, then of course you have the answer to this question. And forget about the n minus 1. It's initially easier to think of n.
Other servers could have pushed the update as well. It doesn't have to confirm with the state it thinks it knows about what's happening at that point.
So, why am I talking about pessimistic here?
Because you assume that every server is going to be less accurate.
Because you're assuming that every server is going to be less accurate.
So every server needs a part of that delta.
Every server is taking a part of that delta, yes. Okay. But why is that pessimistic?
Because it can also happen that one server is actually has done everything, so its view is correct, so it doesn't need to take part of the delta.
Yeah, that's very well explained, actually. What you're saying is that, let's take a look at the truly optimistic one. The truly optimistic one would be that every server would instantly propagate its updates to server SI. Okay? So that means that SI is already actually in a very good state, and only you are, let's say, at most delta units away from that. So in principle, if every other server instantly forwards its updates to SI, you can hold back for delta units. Okay, because in that case, you're still meeting the specifications. Namely, that the total deviation is less than delta. Okay? So what you do is you are pessimistic because you don't know what these other guys are doing. So you know that if you start propagating updates when the deviation is only delta over n, which is much smaller, and you know, this is very important, that every other server will do that as well, then the total aggregated deviation will never be more than delta. And in that sense, it's indeed pessimistic. Is that clear to everyone? Why n minus 1?
Because your own updates are.
You're always up to date. You know exactly where you are. So that means that in your case, this is 0, which means that you can exclude it from what the others are doing. And that's where the n minus 1 comes from. Okay? Now, in the book I also explain how you can do this for staleness, is time, and it's exactly the same thing. I must say this is the easiest explanation of continuous consistency. You can also do this for relative errors. And basically what happens is that the expressions just become a bit more intricate, but the principle is exactly the same thing. Do you guys understand what's going on here? Is this clear to everyone? Yes?
In the formula, should it be the minimum value of delta I if we're working with delta I?
Should it be the minimum value of delta I? If we were sticking to delta I for different servers? No, I don't think so. Because you're only interested in what your specification was. You were allowed to deviate no more than delta I.
If I have a greater delta I and
Okay, I think, yeah, you're right in the sense that it depends on what the specification was for the total deviation of x. If it turns out that that can be at most, and now I should be try to be accurate. If the total specification will be the sum of delta i's, then you're right. Then this should be the minimum. But what I did was, in the specification, I said, I give a specification per server, and then it works.
But I'm calculate this. You need to sum all the contributions from each server.
True.
So if a server has a greater delta I, it will have a greater contribution. And in the case of this formula applied to a server with a lower delta I, then those n contributions will go beyond.
Go up, yeah. So I have to repeat this for the recording. If you take a look at the individual contributions in the deviation from every server, you may actually go up beyond that, beyond what is totally allowed. This is what I just remarked, actually. If you take a look at this specification, I'm telling a server, you are not allowed to deviate by more than delta I units. And that means that the total deviation is the sum of these delta i's. And that's the difference with your assumption that the total deviation cannot be more than a maximum delta, for example. And then you're right, because then every delta I would contribute to that overall view. And then you should have the minimum, you should be even more pessimistic. I completely agree.
So this delta I is not the same as the delta I of the next one?
Yes, it is. But what I'm saying is, to keep matters simple, every server is allowed to deviate by the same amount, namely delta. Delta I is delta for every, delta I is delta, delta J is delta, delta 1 is delta, etc., etc. That just simplifies the reasoning.
Perhaps you meant the delta I divided by n minus 1 here also.
No, I did not.
Okay.
But coming back to your reasoning, what I could have done is say, no, I need to ensure that every server should stick to a global delta over n deviation. Now that's a different specification, because what I'm saying is that servers collectively, you are not allowed to deviate more than delta units. And what I will tell each server individually is, you are not allowed to deviate more than delta over n, you are not allowed to deviate more than delta over n, etc., etc. And then delta I becomes delta over n. But that's not the specification that I gave. And that's the difference in the reasoning between the slides and your reasoning. Okay? What I typically can ask during an exam, and which I did, was to tell me what this thing is all about. Okay, so I will be testing your understanding of the formulas. Or, for example, explaining why this one would save the day, would be good enough, or why it is pessimistic. And to give you another idea, I have also asked, give me the expression for VT or the expression for VI. And basically what I'll be then doing is testing your understanding of the formalities. And the nastiest question would indeed be the one where I say, okay, tell me why this one is good enough. But actually, I feel confident that you guys would actually be able to give the right answer to that. I will not ask you to write this up completely from scratch. That will be ridiculous. I wouldn't be able to do it without looking into the book. So why would I ask you? Okay, and I do believe it's actually nonsense to do that. But I do want you to understand what's going on. Okay. How are we doing on time? I propose that I simply finish the next 5 slides, and then we call it a day, actually. Okay, so this will be a brief one. Don't worry, I may take some time for these slides, because these are important protocols. But they're less difficult than the other ones. Another very important and famous consistency protocol is the primary backup protocol. This is widely deployed throughout distributed systems, and it works like this. And once you understand this, you understand why I can talk about a scale down when you actually apply replication. The whole idea is the following. You have a number of backups. And these are really backups, so you often apply this in the case of fault tolerance, for trying to achieve fault tolerance through replication. And in this case, I have 4 backups. I have a client over here that initiates a write operation to this disk, and it's a local disk. You could also say it's the closest disk, or the one nearest by. Now, watch the protocol. What happens is that this disk, the software, the process controlling that disk, sends the write operation to a primary server. So I'm assuming there's a primary. That one then first contacts every backup to say, hey, there's an update. It gets an acknowledgement back from all the updates. And then, I could have drawn a line over here, that client is allowed to proceed. So when it actually takes this step, so when the system returns with, hey, okay, what do you know for sure?
That the data has been replicated to all the secondary servers.
Exactly. You know for sure that all the secondary servers, the backups, have actually executed the update. So when you get a response, you know you're doing fine. Okay? Your write operation has been executed everywhere. Now you should understand why I could talk about a scaling down of the system if you would apply this widely.
Too many servers probably to a single point of failure because I'm a central one.
No, one thing at a time. And I've argued a number of times that having a single point of failure is much better than having endpoints of failure.
Takes too much time till the client gets an answer if the system is too big. Because the central point has to wait to propagate the answer and then give response.
So that's what I wanted to hear. The primary, this could be a poorly performing protocol because the primary has to get the acknowledgements from n-1 other servers before it will allow the client to proceed. If n is very large, you may have a problem.
Shouldn't you just say, well, if I get m acknowledgements back, I think the data is safe enough to tell the client that it's been saved?
In fact, yes, if m is a majority. I'll get to that in just a minute. In practice, n should be relatively small. In practice, n is something like 3. Okay? Or 5, something like that. Then it may actually work. Yes?
Is W4 and 5 sent simultaneously because they're both sent from the same?
As an optimization, yes, no, whoa. No, they can't be simultaneously.
Okay, but together. It doesn't wait for a response from W4 or anything.
The primary waits until it has all the W4s. The W4s are the acknowledgements.
But then how does the left database thing know when to send W5?
And that's what I mentioned. What I should have done is in this primary, tell this guy over there, hey, I have all the updates. And then W5 can take place. So I could also say that W5 actually proceeds from the primary through this thing back to the client. Okay? So you're right in that sense. When it comes to read operations are great. You go to your local database, you get an instant answer back. So reads are cheap. And you know that this works because we have just guaranteed that all the updates are being propagated to all the backups, so hey, you're safe. Interesting question just pops up. What happens if you have concurrent writes and reads? You should be able to answer this by now. Say this again?
You want to know that the write has arrived in the time while you are reading something from the database.
Okay, so I'll repeat this. You don't know that the write was actually arriving or being processed when you're reading from the database. So what are you saying?
You will read stale data. Eventually, the stale data.
You will be reading stale data. This is an interesting statement, actually. Because from what you just explained, you will eventually always have read stale data.
No, it depends on
What I read today will be stale tomorrow.
if you write and read the same document or the same data.
Uh-huh.
Then depends on what operation comes first. If the write comes first, then it locks the document or the data, and then you will read the new data. Otherwise, you will read the stale data.
Yeah, okay, so you'll be reading just everything that happened just before the write operation, or anything that happened just after the write operation. I wouldn't say that you should be, I wouldn't speak about stale data or not. It is more correct, that's actually a strange statement by itself, more accurate if you would say, well, your read will take place just before or after the write. And from that perspective, you're doing fine. It's consistent. It's called sequential consistency. Okay? Yes? It is?
Yeah, if
No, it is what?
the write and read happen at the same time,
Yep. Concurrently, yeah.
concurrent, it's not a problem.
It's not a problem.
Because it will wait until double time,
No.
the acknowledgement.
As long as the read operation will not return data that is being updated. That's one thing. Now, for sequential consistency, you also have to make...
You get a write log. You cannot read when there's data written.
Yeah, so in practice you will have a write log, okay? And if you combine this with read logs, the system over here may still decide to give you back the value that was there just before the write log. That would still be consistent, under the assumption that there's no backdoor channel by which these two can see what's going on. Okay? So you can have perfect concurrently operating read and write operations. They don't need to bug each other. Okay. This is what you would do with any normal database. This is not what you would do with any normal database. And this is actually called the another name for this is the optimistic primary backup protocol. I call it the primary backup protocol with local writes. Works like this. I'm a client over here that wants to do a write. And what happens is there was this primary, and the first thing what happens is that you actually get the stuff that belonged to that primary. That means that you now have up-to-date data in this database. And watch this. You get an acknowledgement for your write. Then behind your write, behind your back, so to say, this thing starts to send updates to the other databases and waits for the acknowledgements. Do you see what's going on? Yes?
I don't get the W2. Because it shouldn't go the other way.
No, what I'm doing is I'm moving the primary to the client that is doing the writes. And there's a hidden assumption here. And the hidden assumption is, if you're going to do a write once, you'll probably want to do more. So what will happen is that you get the most recent version of the data, and you can do your write operations, and concurrently with your write operations, or even just your single write operation, the backups will be updated. So what's the risk here?
The client cannot be sure that the data is correctly backed up to all, or at least more than one.
Yep. It will certainly not get that guarantee at all. Okay? Is that clear to everyone? This is also...
Shouldn't W1 then go to the old primary? Because now W1 goes to the new primary, and by magic, the old primary instantiates some kind of communication.
Yep. So, depends on the implementation. If if this is the interface to your system, I now implemented it by going to this database, and then this database takes the initiative. The middleware could also say, well, bzzzt, and then, you know, it really depends on how you would implement it. But that's an implementation issue. Yes?
If you have some kind of problem, if you have like 3 clients working on 3 different databases, all writing a lot, because you're shifting the value.
Okay, that's an interesting one. Suppose that, okay, I have here a reading client, and I can apply the same scheme with the primary or backup protocol here. The reading client can just go to the local database and fetch what's in there, okay? Would I have a consistency problem?
Like you said, if there is no bad channel, there is no consistency problem.
Exactly. You will get sequential consistency.
But if they're both writing it.
Okay, but if they're both writing, I'll get to that in just a minute. Okay, so it's no problem that this guy over here gets whatever data as long as it was consistent with what it perhaps saw before. Or, very important, it's not redirected to one of these things over here, because then it will see strange results. So if it sticks to this one, you're fine. Yes?
Yeah, that was my question, if the clients move things that fine.
One thing that I will make a selection out of the stuff that I want to talk about when discussing web-based systems, and this is in particular one important one. What you often see in web-based systems, that if there are replica servers, you are always directed to the same one, you as a client, for good reason. Namely, to maintain your consistent view on the data. But if you go to another one of these edge servers, hey, wait a minute, that was not supposed to happen. Okay, now let's have 2 writes, 2 writers. So this client over here can in principle also be a writer. Then what?
He may not have the latest update, because the first, both of them will get the information from the primary server, and then maybe one of them updates with the primary server before the second one.
So one will become the primary. Okay, so let's say that this client over here now becomes the primary, or can act on the primary. What this protocol implicitly assumes is that you are only allowed to operate on the primary when you're a writer. So if you're also a writer, you need to make sure that you become the primary, right?
Then that's fine.
And then it would be fine. And then, I think you mentioned it, you could get into a heavy-duty performance problem if that stuff is being swapped between these two. And that's when you get into write locks. Okay? You say just hold your horses, somebody's over there. If I introduce locks, then at least I can know for sure when this guy is done, and then you pass on the protocol to the others. So the drawback would be that if you want to maintain sequential consistency, a writer over here would need to wait until this writer is really done. And that may be costly.
Global write would be quite costly.
A global write in these type of systems is costly. And as I will explain next week on Wednesday, because Tuesday we won't have classes, I'll be talking about the Paxos protocol. You'd be surprised how costly it can be. But computers are fast. Yes?
But you can basically move the primary already after returning W3 to the client. You return to the client, say, right, your write is done, I'll handle the backend. And before it starts doing W4 and 5, you could already hand off the primary to the left one and instantiate another write.
Absolutely. So what you can do is, let me repeat your question. So let's just optimize on writes. Everybody does a single write, okay? Then in this scheme, you are allowed to do the following. A writer over here, you move it to the primary, you do the update, you do the acknowledgement of the write. You have a writer over here, and the first thing you do is you move it over to that database. You let the writes happen over there. And then if there's another writer, you move the primary again. And then after a while, when you say, hey, you know, it's becoming a bit lazy in my system, let me start replicating this stuff. It's basically a form of lazy replication.
But you also have to move that you didn't get the W4 for yet. And it's already been applied to the data he's getting.
So that will be good. So if you do that, what would be a typical form of replication you would do if you let the primary move all the time? The answer is obvious at the instant I mention it. And I mentioned it yesterday, that you had two forms of replication. Active replication and passive replication. The difference was in active replication you move operations, and in passive replication you move the entire data. You would do passive replication. So you would just let updates take place for a while, and when the whole thing is settled down, apparently no writers, you really propagate through passive replication the updates by overwriting what is in the other updates. That will be fine, and then everybody's in the same state. Okay? No failures. That's next week. Okay. This is actually an interesting example. From a certain perspective, this is what you would do with mobile computing. And operating a so-called disconnected mode. So this laptop is now operating in disconnected mode. And what I did is, I fetched stuff from my database. You know, this is what's out there. And then later I could do modifications over here, and then I would hook it back into the system, and I synchronize everything. And let's just hope that nobody else was working on my data. Okay. Now, last slide. Quorum-based protocols. I must say I always used to be quite cynical about this, and actually I am still quite cynical about this, in the following sense. There have been a gazillion papers on quorum-based systems. Most of them are theory, and they have never passed beyond theory. But that is exaggerating a bit, because, for example, next week I'll be talking about the Paxos protocol, and this is where you see that you can use a majority, and it actually makes a lot of sense. Okay? And there will be other examples where talking about a majority is actually very sensible. Now, what's the whole idea? You talk about a read quorum and a write quorum. Now, the strict definition of a quorum is a subset. In distributed systems, it means something like a majority. Okay? So quorum and majority are two equivalents. And the whole idea is that you have a bunch of servers, and you ensure that a read quorum always overlaps with a write quorum. For a very simple reason, then you always know that you will be seeing the most recent data. To make this very specific, I will talk about the number of servers you need to contact to do a read, plus the number of servers you need to contact when you're doing a write. That should be greater than n, the total number of servers. If I guarantee that, then I will be guaranteeing that any read set will always overlap with a write set. Okay? To give you an example, there's one other constraint I'll get into just a minute. If my read quorum is 3, I have 12 servers. If my read quorum is 3, and my write quorum is 10 plus 3 is 13, there is no way that if I'm a reader, I will not be touching a writer to which I had sent an update. That means that as a read set, I always will be seeing the most recent write. Is that clear to everyone? Here's another example. I have this write set over here that consists of 6 writers. And my read quorum is this thing over here, which consists of 7 readers. So this guy, this read set will always overlap with one write set. Okay? No? Not okay? Why not okay?
We can have 2 writers.
Ah, yeah, that's this condition. Okay? This other condition, I'm going to disappoint you because this is the last slide I'll be discussing for today. I'll remove that from the recording, by the way. But So this is the second condition, which is very important, that the write set needs to be larger than half of my total set of servers. And you can explain why.
Now we can have two writers writing on the same data at the same time.
Be more accurate.
Well, in this case, you can have two writers.
Not two writers. Well, you could have, okay,
Write operations.
two write operations.
And they can write at the same time on the same value, so you don't know what the value is going to be.
So you can have two non-overlapping write columns.
That's what I wanted to hear. So you understand what, you're correct, but you didn't formulate it correctly. So if I would stick to just that the write set would be allowed to be equal or less than the server set, then in this example I could have this write set and this could be another write set. And now I'm in trouble, because in that case I would have two subsets, non-overlapping, which could now gradually evolve into completely different values of the thing that I'm updating. Okay? And even if my read set would overlap both of them, I would just see, wait a minute, conflicting operations. Now this is a special case. This is always where I get a bit agitated, not for very good reason actually. So my write set is now 12, it's all of the servers, and I have one. My read set is always consists of one. This is called ROA. It's just another term. Read one, write all. And it's also called no. Primary backup protocol? Yeah. Time to get agitated, right? Why ROA? I thought this was almost the same as a primary backup protocol. And in fact it is. Okay, is that clear to everyone? And this is a very common scheme for very good reasons. Why? Because writes generally, generally, in many, many cases, you have more reads than writes. So this is the reason why you would do that. Next week I'll be talking about a different type of system where you see that you do need majorities, quorums, but for completely different reasons. Okay, so watch this. I can stop it